Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. We are in chapter 12, part 1. All right, so we've been talking about our linear regression models where we have y equal to beta 0 plus beta 1 x1 plus all the way up to beta k xk plus epsilon. So we're in multiple linear regression. Now, if we want to just talk about the interpretation of a single slope for one of the betas, we could think about two situations. One where we hold all variables in the model constant, but we just increase our value for xj by 1. So let's think about two different predictions. So in the first case, all right, we're going to have y hat equals beta 0 plus beta 0 hat plus beta 1 hat x1 plus all the way down to beta j hat xj plus keep going all the way up to beta hat k xk, right? And in the second situation, I'm going to get a prediction. So this is going to be my first prediction. And then in my second prediction, so the prediction 1 and then prediction 2, I'm going to get beta 0 hat plus beta 1 hat x1 plus dot, 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 all the way up to beta j hat. And then I'm going to increase my xj by 1 unit. So xj plus 1, and then all the way down to beta hat k xk. And if I take the difference between these two things, you'll notice that the difference between my second group of predictions and my first group of predictions, and if I wanted, I could just redo the notation to say the expected value of y given x j plus 1 versus the expected value of y given xj, right? So if I take the subtraction in these two things, everything is going to cancel out, right? The beta 0 hat minus beta 0 hat is going to be 0, and the beta 1 hats x1s are going to cancel out. Everything's going to cancel out except for I'm going to have beta hat j xj plus beta hat j minus beta hat j xj. So at the end of the day, I'm going to just be left with beta hat j. All right. So this helps us with our interpretation because we can see that the difference between our prediction when we have xj versus our prediction when we increase xj by 1, that difference is going to equal the slope, okay? Another way to put it is that we can say a 1 unit increase in xj is associated with a beta j unit increase in y on average when all other x's in the model are held constant. This would be if the slope, if our beta hat j was greater than 0, right? But if our estimated slope coefficient is less than 0, then we say a 1 unit increase in xj is associated with a beta hat j unit decrease in y on average when all other variables in the model are held constant. Okay, we have to hold all other variables in the model constant because otherwise when we do the subtraction, they wouldn't cancel out. Okay, if our associated variable is a categorical variable, okay? Let's cross out dummy and say categorical variable, okay? Then we have to interpret the beta hat j slightly differently, okay? And we're gonna do that in a future lecture video. So really, we can only do this when we have quantitative xj for this interpretation we're talking about when our variable is continuous. So let's think about if we were talking about BMI, body mass index, and some measure of lung function, say forced expository volume for our Y. So we're going to say a 1 unit increase, right? A 1 unit. Okay, so BMI, we should think about what BMI is measured in, and you should fill in that measurement for BMI. A 1, I'll keep it blank for now, a 1 blank increase in BMI is associated with a blank increase or decrease, depending on if that beta hat J was positive or negative, in FEV1, right? So this is measuring the relationship between BMI and forced expository volume in 1 second. So when we go and talk about that relationship, then we plug that in. So whatever units you have, you should fill in here, and whatever your beta hat J is, you should fill in there. So you have to fill in the units. This is something that you would have to look up and make sure that you know the correct units for BMI. All right, linear in the betas. Remember that in the last video we talked about that our betas are never raised to a power. So we have linearity in our betas. We can always have interaction terms of or powers of the x's, but we cannot do that with the betas. Okay, our model assumptions are that our epsilon i's are independent. So that means the random error with the first person will not affect the random error of the second person. So your patients couldn't be like within the same family. They couldn't be siblings because then their responses might be related, right? Once you know that someone in their family has lung problems, it might change the probability that someone else would have lung problems. So you want independent subjects. Your epsilon i's, they are distributed with a normal distribution with a mean of 0 and a variance of sigma squared. So when you do your residual plot, we should see residuals that look random. If your residuals don't look random, then you probably need to look into that and figure out how you can fix your model.